Okay.
Can you guys hear anything? Okay.
Good morning and afternoon. My name is Janie Montblanc, and I'm the Great Basin Science Delivery Project Coordinator. Welcome to our webinar titled Climate Change, Climate Variability, and Ecosystem Response in the Great Basin, presented by Ann Heinsch from the Rocky Mountain Research Station, Missoula Fire Sciences Lab in Missoula, Montana. If you have questions at any point during the webinar, you may send me a direct message by expanding your control panel on the top right of your screen to access your questions pane. I will show up as the Wildland Fire Lessons Learned Center. You can also click the hand icon in your control panel to raise your hand and I will text you a response. If you have questions for our presenter, you're welcome to type them in at any time, but I will field the questions at the end of the presentation. Now I would like to introduce our presenter. Ann Heinsch is a research ecologist at the Missoula Fire Sciences Lab. She has degrees in geography, German, atmospheric sciences, and soil science. Most recently, she worked at the University of Montana investigating the impacts of climate change on vegetation growth. She worked on the validation team for the moderate resolution imaging spectroradiometer gross net primary production model, and helped develop modifications to the biogeochemical cycles ecosystem process model for application to a variety of ecosystems, including croplands, the Arctic tundra, and the Chequamegon Ecosystem Atmospheric Study Site. Her research at the Fire Lab focuses on fire behavior, especially Behave Plus, and the National Fire Danger Rating System, as well as climate change research, education, and outreach. Welcome, Ann, and thank you for being here today.
All right, thank you so much, and I apologize again for the computer snafu, but I think it's working.
All right, I have just made you the presenter.
Okay, so we'll show my screen.
Great.
And all right, hide the control panel. So does that show up?
Yep, I can see it.
Okay, excellent. Thank you. So thank you very much for that really thorough introduction. I always forget all the stuff I've done in the past. So the first thing I want to talk about when we talk about climate change is to differentiate between weather and climate. So back in high school or college, we looked at things such as weather is that meteorological conditions from the next day to the next couple of weeks to months. And so, for example, today in Missoula, it was below freezing this morning, and it's warming up slightly this afternoon. But our climate is the long-term average condition. The National Weather Service uses 30 years, the past 30 years, to determine what the average climate is, and then you compare this year to that past climate to see how it's going. So weather is that short-term day-to-day, climate is the long-term analysis. But that doesn't always get it across to people in a way that I think really demonstrates what's going on. So I have another method that I like to use, and I say on any given day, if you choose shorts or long underwear, then you're picking your weather. So you go outside, you see what the weather is, and you pick the clothes you're going to wear. But if you look in your closet and you count up the number of pair of shorts you have and the number of pair of long underwear, that's going to be your climate. So someone in Alaska is probably going to have fewer shorts than someone who lives in Florida. And so we have some built-in expectation of what our climate is, and weather is what happens that we average together to get that expectation. Another thing that I need to mention is I hear a lot that the atmosphere is so incredibly huge, there's no way we could have any impact on it. So to put it a little bit in perspective, the Earth is almost 8,000 miles in diameter. And the atmosphere is much, much smaller than that. And in fact, if you take an orange and consider that that's the Earth, if you scrape just that little orange zest off the top, that's the equivalent of the atmosphere's depth in respect to the Earth. So really, as if you look at the Earth as a whole, the atmosphere is fairly small, and the active weather occurs in the bottom 8 miles of the atmosphere, and it goes out about 100 miles. One of the best tracer experiments we've ever been able to employ and use to our advantage was when Mount St. Helens erupted in 1980. And at this point, scientists, being scientists, said, wow, let's just see how long it takes this cloud to get around the Earth. And it takes really about 10 days. It took about 10 days for this cloud to get around the Earth and back to the mountain. And at this case, that gives us an excellent idea of the memory of the atmosphere itself. So the atmosphere really has a memory of about 2 weeks. You're not going to be able to forecast much longer than that in terms of weather, simply because the atmosphere itself isn't designed for that. On the flip side, the climate is dominated by the ocean system. And this graph shows us what they call the Great Ocean Conveyor Belt. It's the oceanic circulation patterns, and the blue are the deeper circulations, and the orange are the warm surface currents. And so what happens is you have, let me get the arrow out, you have something that moves into the current, and then at certain places around it will dive down and move into the deep ocean current, circulate around, and at other areas come back up to the surface. And it'll repeat this entire cycle. This cycle takes approximately 1,000 years. And so weather is much more affected by these long-term climate is much more affected by these long-term processes, simply because the ocean is what determines our climate. Moving back to the atmosphere, one of the theories behind climate change was begun by, they were searching for the ice ages back in the 1800s, and John Tyndall in 1859 demonstrated that carbon dioxide actually absorbs energy. And he was trying to explain the ice ages and what caused them. In 1896, Svante Arrhenius, a Swede, published his theory for the ice ages, and he, once it was demonstrated through the laboratory experiments, he created the theory behind how it actually works. So solar energy comes in at a very high solar radiation, passes through the atmosphere, and once it hits the surface of the Earth with its short wavelength, it gets absorbed and then re-emitted in the long wave. And this long wave is in the infrared spectrum. And the infrared is what actually gets absorbed by your greenhouse gases. And so your greenhouse gases, such as CO2, nitrous oxide, those will absorb the infrared radiation, and then they'll re-radiate that in the form of heat. Now, the greenhouse effect is a good thing, because if we didn't have any greenhouse gases in the atmosphere, the Earth would act a lot like the moon. It would be very, very cold at night when there is no sun, and during the daytime it would be very hot. So the greenhouse effect serves to actually maintain the Earth at a fairly constant temperature. What happens when you increase the number of greenhouse gases in the atmosphere is you then increase that absorption and re-radiation, which heats the atmosphere and therefore the Earth. And then once the oceans begin to warm up, then you're going to move into changing the climate. One of the ways that we know that atmospheric CO2 is increasing was started by Charles David Keeling for his postdoctoral work. And he set up a system at Mauna Loa Observatory in Hawaii. He was looking at the clean air in the atmosphere. And his idea then was to measure the CO2 concentration in the atmosphere. And they weren't quite sure what they were going to find, but they wanted to find a baseline. Within a very few years here at the beginning, they found a couple of interesting things. The first thing is that there's this seesaw effect in the CO2 concentration, and this is driven in large part by the North American seasonal cycle. So in the summertime, plants in the northern hemisphere are photosynthesizing. They take up CO2, and the CO2 in the atmosphere declines. In the winter, they move out of that cycle, and the CO2 will increase again in the winter. And then we have the photosynthesis and the turning on and off of photosynthesis throughout the year and the seasons. The other thing that they noticed is that it was rising with time. And we can see as we continue on, once we get up to 1910, which is the last record that we have right at this moment, we're up around the 390 parts per million level. So we can see there's definitely been an increase. The question then becomes, what is causing that increase? So as of September 2011, the atmospheric CO2 concentration was 389 parts per million. and that's 39% above pre-industrial. And the graph on the right-hand side shows you very clearly that seasonal trend of the photosynthesis in the northern hemisphere turning on and off. And that's because we have more land and therefore more vegetation in the northern hemisphere. On the lower left, we also see that there are a number of years. You can see what the trend is for how much the CO2 is rising per year. So in the 70s, it rose by 1.3 parts per million per year, and in the 2000s, it was 1.9 parts per million per year. In 2008, because of the recession, we did have a decrease in the amount of increase, but the CO2 concentration still increased in the atmosphere. And then in 2010, this is the largest growth to date, and the atmospheric concentration was growing by 2.4 parts per million per year. At the same time, fossil fuel emissions are also growing, and they're projected in 2010 to grow at greater than 3%. Right now, the emissions of CO2 from fossil fuel is about 8.4 picograms of carbon, which is 10 to the 12th grams of carbon. And so it's increasing with time. So we can overlay that with the graph of increase that I showed that Dr. Keeling started, and we can see that a large part of that is due to fossil fuel emissions. Another portion of that, and this 7.7 here, is what it was in 2009. So this is 2000 to 2009 in this graph. So there's your fossil fuel emissions. We also have land use change, and this can be in the form of converting from a forest to agricultural fields or from agricultural fields to forest. It can be deforestation or cutting down forest, or it can be regrowing forest. Anytime you take carbon from a forest through deforestation or land use change, you're going to release carbon into the atmosphere, and when you're growing forests again, because they use much more CO2 than other plants to photosynthesize, then you're going to decrease that. And this rate has actually been going down. So land use change, there's a lot less of the massive deforestation and conversion to agricultural land. So this amount is much smaller than it used to be. The next question we want to ask then is, we have all this CO2 going into the atmosphere, and the atmosphere can't account for all of that. So we look to see where it's going. Well, we know if we have these emissions, about 47% of it ends up in the atmosphere. So what happens to the other 53%? About 27% of it is absorbed by the land, either through the vegetation or through soil or in some other method, but it's taken up and absorbed by the land. Most of it is taken up by your forested systems. Another 26% is absorbed by the oceans and through chemical processes there. And so that's pretty much where it goes. So we have about a quarter of it going into the oceans, about a quarter of it going onto land, and then about 50% of our emissions every year end up in the atmosphere, which is why our atmospheric CO2 is increasing. When we want to model climate change, the first thing we have to do is make sure we take into account not only the emissions that warm the atmosphere, but also those things that cool the atmosphere. And so we have a number of gases here that we look at. We look at carbon dioxide, methane, and nitrous oxide, which are long-lived gases in the atmosphere. We look at ozone, tropospheric ozone here. And then we look at land use change. If you have black carbon, which some of you may have heard of, on snow, that's actually going to absorb energy and raise the temperature. But a lot of our land use, now that we're reverting back to forest, is actually going to cool the system. And then we have our aerosols, sulfate particles, clouds, things like that, which by and large are going to cool the atmosphere, particularly if the cloud particles are those small cloud particles. The sun itself has a very small effect on what we're seeing in the atmosphere. And so if we add all of this up, all of the impact that we have between the natural and the anthropogenic, the total anthropogenic effect is about 1.6 watts per meter squared. Now that doesn't mean a whole lot to most people in terms of units. So I want to give you an analogy here. 1 watt per meter squared is about the heat energy released by one of the Christmas tree lights that you would have on your tree. So each light on your tree, if you feel the warmth coming off of it, that's 1 watt. And so 1.6 watts per meter squared is like taking 1.6 Christmas tree lights and putting them in every meter squared of the Earth, and then feeling the heat that's coming off of them. And that's the warming that we're seeing from this. CO2, because it's long-lived in the atmosphere and because of the amount that's being released, causes the bulk of the anthropogenic emissions, and that's why when we look at things, we always look at them in terms of their CO2 equivalent. Okay, so that just shows some of that. Now let's look and see how the Earth is responding to the changes, both natural and anthropogenic, with time. This graph shows on the bottom the past 1,000 years in the Northern Hemisphere. The blue line, the dark blue line, is the average over time. And if we look in the gray here, up until about the 1850s or 1900, that's proxy data. We don't have direct temperature measurements around the world, so we use things like tree rings and ice cores and boreholes to infer what the temperature must have been. And as you move back in time, you have wider and wider error bars because you're less certain about your temperature. And then we just smooth those measurements, which are the light blue, over the dark blue line. Once you see the red line begin around 1900, those are our direct temperature measurements. And we use those and compare those to the proxy data that we know so that we can infer the temperature relationships that we can then use back in time. But we can see as we move on that temperature is increasing. If we look just at the past 140 years or so, this takes what we look at here as a departure from an average. So we took the 1961 to 1990 average, and then we looked to see if a year was colder than that, such as prior to 1940, or if it was warmer, such as during the Dust Bowl era and World War II. Then we move back into a cooler period and again into a warming that's been sustained since about 1980. The cooler period between 1940 and 1980 has a lot to do with a concept called global dimming, and I can answer questions about that later if you'd like. If we look at a number of different units, there are a number of people who use data around the world to get this information. The Hadley Center in Great Britain, NOAA has the National Climate Data Center, and then NASA's Goddard Space Institute. All of them use slightly different collections of meteorological data from different stations around the world, but all of them show very, very similar trends, and we see this dramatic increase since about 1980. In fact, the warmest years on record, 2010, even though it was very mild, at least here in the Northwest, was tied for the warmest year on record with 2005. 1998, 2002, 2003, 2006 and 2007, and 2009 are all tied for third place then. Statistically, there's a little bit of variation in there, but by and large, our warmest years have all happened since 1998 on record. And in fact, 2010 was the 34th consecutive year that global temperatures were above the 20th century average. So if you take average temperatures for 1900 to 1999, this is the 34th year in a row the temperatures have been higher than that average. One of the other things that comes up quite a bit is when we talk about global temperatures versus local temperatures. And so in this example, I have on the left U.S. temperature. And we can see that 1938 was an extremely warm year in the United States, and some people have proposed that 1938 is actually the warmest year on record. It was very close to 1998, and it's about 1/10 of a degree cooler than that, and I wasn't able to update this to 2010. However, if we look globally, I've circled 1938 in blue, and we can see that while in the U.S. this was an extremely warm year, globally, it really wasn't that warm of a year. And so when we're talking about the global temperatures, which is what I've been talking about most, we can see that some of these anomalies we see in different countries around the world may or may not be reflected in that global trend. If we look across the United States, we can see that the West is warming, as is the Northeast. And there's been a slight cooling trend in the Southeast from 1901 to 2008. Most of that occurred before 1970. Since 1970, the South has been warming ever so slightly, but not enough to offset that cooling. We also see that warm nights are increasing and cold nights are decreasing. So in essence, what this tells us is if we look with time, we've got 1901 to 1950 on our cold nights, and then if we go to 1979, we can see that there are fewer and fewer nights that are considered cold. And then if we look at the warm nights, we see the reverse. Looking at precipitation trends, drought is increasing in most places around the world, and we'll discuss that more for the western U.S. in a minute. But generally speaking, we mainly see a decrease in precipitation over the tropics and subtropics, and that's mainly due to the fact that the atmosphere is warming and can hold more moisture. If we look at the U.S., it's very difficult to predict precipitation, so these are actual measurements of precipitation. We can see it's kind of mixed. Some places are getting much drier, and other places are getting wetter. By and large, we found that places that are already wet are getting wetter, and places that are already dry are getting drier. Now, this is some research that I just showed last week at a meeting, and I wanted to show you in particular. I want to focus in on the stations in the eastern Great Basin. What I did was I took some fire danger rating stations, which we use remote automated weather stations. So these are away from cities, up in the mountains, and I looked to see if they had a minimum of 30 years of data, and I only looked at the summertime weather because that's all the data that I had. If we look at the maximum temperature with time, we can see that there has been an increase beginning about 1993 in temperature. We can also see that there's a little bit of a cycle going on in here, and I'll talk about that a bit in a minute. Minimum temperature has been interesting because it almost seems like there's been a step change between the lower temperatures and the warmer temperatures that we've seen recently. Relative humidity has a much clearer signal. And it's been definitely getting drier in the eastern Great Basin since sometime in the 1980s. And the precipitation really hasn't changed that much over the summertime months, so we can't explain it from precipitation itself. Largely it's due to the increase in temperature. So we have a warmer temperature, which gives us a net decrease in the humidity. In terms of precipitation duration, this is how long each storm lasts. This graph shows us the number of days it did not rain in June through September of any given year. And we see that there's an increase in the number of days with no rain since about 1995. Again, there's a cycle here, and one of the cycles that I want to examine next, this is all preliminary research, one of the cycles I want to examine next is to look at the El Niño Southern Oscillation, or ENSO cycle, and see how that then affects the trends that I'm seeing here, as well as looking at just the trends and assuming that they're associated with something else. So we're going to check that next, and stay tuned. What about the hydrology on a regional level? Well, if we look across the West, we see that the minimum temperatures from January to March are increasing with time, and that's in the middle graph on the right here. And we're seeing that more, this top graph shows us the ratio of how much rain, how much of your precipitation comes as snow. And so it's decreasing with time, indicating that we're getting less precipitation as snow. More of it is coming as rainfall. It doesn't mean we're getting less precipitation. It just means that we're changing the form from snow to rain. And this has resulted in an earlier a change in the river flow so that our rivers are peaking earlier. This is another way of looking just at the western region. You can see there's a small portion of the Sierra Nevadas in which there is an increase in the amount of snowpack in the spring. This is the April 1st snowpack measurement here, and we see that by and large, except for the lower Sierra Nevadas, there is a large area in which there is less snow on April 1st than there has been in the past. This down here in the Sierra Nevadas has to do with changing ocean circulation patterns and is not related necessarily to climate change. It's also not statistically significant. The other thing that we see is not only is there less snowpack, but it's melting earlier, and on average the snow season in California and Nevada is about 2 weeks shorter than it has been in the past. If we look down more in the southwest into Arizona and New Mexico and Southern California, there's certainly been a large drought, and this will come as a shock to no one on the call. But what we've seen is that this is actually part of a longer pattern of drought that has happened in the past, and some of the droughts in the past have been more severe, and they're marked by the black arrows, and have lasted longer than the one that we're experiencing now. And this comes from reconstructed flow of the Colorado River using tree ring data. And then the red line here at the end shows our actual measurements that we've been able to have on the river, and so that then correlates with our proxy data so that we're more confident in the inferences. The computer models of future climate indicate that in the future we're going to continue to have droughts, and they're going to be hotter and more severe with time. So how is the biosphere responding? The first thing is there's been a change in the frost-free length. So if you're a gardener, this can be good news, because in the Great Basin you've got about 8 days longer of a growing season or frost-free length for your gardens. And here in Montana, that gives us a better chance to ripen our tomatoes somewhere besides our garage. So across the U.S., this change has been about 10 days. And certainly the biggest impact has been in the West, Nevada, Idaho, Oregon, Washington, and California. That's where they're seeing the biggest changes in their frost-free length. All of this has led to changing the phenology. So in the DC area, in 2000, 89 of 100 plants bloomed about 5 days earlier than they had been in the past. North American tree swallows are laying their eggs earlier. There's an earlier arrival of migrant populations, particularly birds, and this was seen across the United States. And again in the Northeast, lilacs are blooming about 4 days earlier than they had at the beginning of this study, which was in 1965. So we're seeing that plants and animals are all responding to these changes by changing how they respond. If we look globally, we can see that by and large, when precipitation is not a limiting factor, plants are responding positively to the increased CO2 and the warming temperatures by increasing their growth and photosynthesizing more, taking up more CO2. So these green areas here show areas in which the net productivity or the amount of CO2 stored in the plants has increased, and the red shows the areas where it's decreased. These red areas are primarily the result of drought. Since 2000, there have been some interesting results coming out. Some models suggest that the terrestrial NPP hasn't changed that much, so we're not seeing these positive responses that we've seen in the past. Some have shown a slight decline because we've had a number of large droughts around the world, but none of these seem to be statistically significant. So I think at this point, all we can say is that plants, when water is available, are going to respond positively if they can until they reach some limiting factor. Another thing that we're seeing more of, although not this year in the Pacific Northwest, is fire. And these just show a number of satellite images of fires in Montana and Idaho. This is 2000, and you can see the smoke plumes. Here's 2003, which was another large year, 2005, and then 2007. We haven't had much up here in terms of fire since 2007, but other parts of the country certainly have. So one of the questions that I get quite a bit is, does climate change actually cause wildfire? The simple answer to that is no, because it does not start wildfires. If to start a wildfire, you need an ignition source, and that can be arson accidents down power lines. It can also be lightning, and these are the main causes here. So you have to have an ignition source in order to start your fire. However, you do have to have fuels that can burn. And so for now, we're climate change does not start your fire. So what we want to do is ask another question, is how is climate change likely to affect wildland fire? And this becomes more a question of fire spread, and that has to do with the fuel conditioning and the moisture in the area as well. This graph shows us wildland fires burned across the 11 western United States from 1916 until 2007. There's a number of things happening in this graph. First, we see there were a large number of fires early on, and then there was an era here where there was a low number of fires, followed by a number of large fires again. A great portion of this is due to management. This was the time during which fires were suppressed, and so therefore the number of acres burned is going to be much lower. Since about 1980, fires have gotten larger. That's in part due to the fact that we've reduced the amount of suppression and we've allowed some to burn. On the other hand, we've also had a number of fires that we could not control. And so there's a mixed message in here, or not a mixed message, a mixed signal in here that has to be teased out, and people are still working out how to do that. So Jeremy Littell did a study back in 2009 to determine how much of fire area burned could be directly related to climate. And he found that somewhere between 39 and 64% of fire area is related to your climate. In the northern Rockies, this has to do with low precipitation and high temperature, just preceding or during the year of the fire. In the Great Basin, we have to have low precipitation the year prior to the fire in order for there to be a severe problem. And in the southwest and more arid areas, generally you have to have moist conditions the year before, because these areas are largely fuel limited. So you have moist conditions that allow your fuels to build up, and then you have your hot, dry conditions which are likely to increase your disturbance. And this picture just shows an example of what impact drought can have. In the top photo, this is the Jemez Mountains in 2002, and this was a pinyon pine juniper forest. And in 2004, the pinyon pine had pretty much all died out, leaving the juniper behind, which are the green in between. And this really changes the ecosystem, because you've moved from an ecosystem that was co-dominated to an ecosystem that is predominantly juniper. Another thing to look at is the insect infestations, and certainly this graph is dated. This is from 2008, but this shows the spruce beetle, the mountain pine beetle, and the pinyon ips, and I will tell you that the beetles on the side are not to scale. So what we see with time is that we've definitely seen an increase in the amount of beetle attack in the western U.S., and there are a number of causes for this. The contribution that climate change makes is that beetles are able to complete their life cycle in a single year, and so there are likely to be more of them out there. But also we have to take into account the fact that the trees are at an age in much of the West at which the beetles prefer. And so we really, when we look at this, we're looking at what climate causes. It really speeds up the life cycle of the insects. And then because we don't have those severely cold winters, we're not killing off as many of them in the winter as we might have before. What it really comes down to in the end is a water balance issue. We know that temperatures are going to increase with time. If we get more precipitation accompanying that temperature, and it's very difficult to estimate the precipitation into the future, we're going to see more productivity. These are the measures of that, leaf area index and productivity. We'll see higher stream flows. With those stream flows, because more will be coming as precipitation, we might see an increase in stream bank erosion. We could see an increase in insect-borne diseases. Some people are concerned about malaria. Human health could become an issue. On the flip side, we could see improved wildlife habitat and increased biodiversity in some areas, because we will have warmer temperatures, so other species can move in, and we'll have the water to maintain them. On the flip side, if our precipitation decreases, then we're looking at things such as pest epidemics, increased wildfire, increased forest mortality, lower productivity, and we're not quite sure what's going to happen with biodiversity, although we think it's going to decrease, primarily because of the number of species who can outcompete your native species. So very quickly, we can look at the next 100 years. Now these are projections, model projections here. The IPCC is our International Panel on Climate Change, is looking to do their next set of climate runs in the next year, and so these predictions will change, and they'll be publishing their report in 2013. So this comes from the 2007 report, and we can see that there's a range of, depending on the model that you select, there's a range of possibilities. The best estimates of temperature increase are somewhere between 2 and 4 degrees C above the 2007 level by 2100. And this is assuming that the CO2 range increases by about 250 to 700 parts per million. The full range of temperatures that we could see are from 1 to 6.5 degrees C, but the most likely range is right around 2 to 4 degrees C. This graph just shows us that we're seeing with this an increase in precipitation intensity, so we may see fewer storms, but those storms will have more intense rainfall associated with them. And we can also potentially see an increase in the number of heat waves and record-breaking temperatures around the world. When we look at extremes, the one thing we're looking at is how is our average climate changing. What we have here is a bell-shaped curve showing the distribution around the average. So here's our average, and then we can either be higher or lower than that depending on the weather at any given time. When we look at climate change, we're actually looking at shifting that mean. And when we do that, things that were fairly rare, such as a 1 in 40-year event, become a 1 in 6-year event, simply because we've increased the temperature and shifted everything over. So therefore, our effects, we're going to see much more change at our extremes than we are near the mean. In the west, it appears that things are going to be about 3 degrees C warmer specific to the west, and the winters are going to be a little bit wetter and the summers a little bit drier. This is a little bit, the precipitation is a little bit more mixed on what they expect to see because it is so hard to model. The temperatures, on the other hand, they're fairly certain that there is going to be an increase, and it ranges somewhere between 2 and 5 degrees C, probably around 3 degrees C or 5 degrees Fahrenheit warmer. If we look specific to the southwest, there's 2 different emission scenarios. This is if we lower the CO2 emissions from what they are today, and this is if they're much higher than today. And we see that in both cases we're looking at a decrease in precipitation, but that higher decrease is going to lead to, that higher emissions is going to lead to a much drier southwest in the future. Again, it all comes back to the water. We're going to have most likely increases in temperature, but what is going to happen with the water? That's the question that we're going to have to ask. So how do we look at this? Well, this graph shows us one way of looking at climate change, and how are we going to look in the near future? We're going to see new fire regimes, perhaps more frequent fire, more extreme events. And then in the longer term, we're going to see habitat changes across the landscape, both for plant and animal species. So the species response, we're going to see fire-sensitive species decrease. Our annuals and weedy species are likely to increase. And those specialists that have very restricted ranges are likely to decrease. And this all comes from McKinsey in 2004. So how do we manage for this? Current management strategies, a number of them presume that the past is a good indicator of the future. But the future is not going to echo the past. That's the one thing we can say. And managers and researchers are currently working to redefine strategies that are not based on looking at the past as a predictor. The best focus that we can have right now is healthy, resilient ecosystems, not looking at specific vegetation types being there, but looking at regeneration and restoration where possible. We're going to have to consider both adaptation and mitigation. And so our research strategies need to include managing with climate change. No single solution is going to fit all the cases. We need to look for a range of options for both short and long term. We're going to have to mix and match tools. Tools that work well in one area are not likely to work well somewhere else, and you're going to need a number of tools everywhere. We need to learn to be a little bit more flexible and innovative. We have to be experimental a bit because we're not quite sure where things are going to go or how they're going to respond. So unfortunately, when it comes to climate and vegetation models, we need to take a healthy skepticism. The managers, I know, need very accurate estimates of what's going to happen in the future, and there's no way we can predict that with the accuracy you need. So we're looking at bet hedging strategies and not putting all of our eggs in one basket, and Connie Millar from the Pacific Southwest Station says this quite a bit in her talks. Some of the other things that have come out of reports, you may look at aggressive thinning and surface fuel treatments, including prescribed burning, to modify your fuels and reduce severity in wildfires. But this is going to be challenging to implement on a scale to have a lot of impact. But if you have areas with high resource or economic or political values, then these are areas that you would want to focus this in. Additional management options coming from both Linda Joyce and Connie Millar: maintaining biological diversity, planning for post-disturbance management, implementing early detection and rapid response, managing for realistic outcomes, and incorporating climate change into restoration planning. So when you're going to restore something, take into account that the climate may be very different when these plants mature than they are now. We need to, unfortunately, be able to anticipate big surprises: mega droughts, larger fires, species movements, and local extinctions, and incorporate those events into our planning. And I'll leave you on this screen with a number of resources that I used particularly to get the management ideas for this talk. And with that, I can take any questions.
Okay, thank you so much, Faith. Ann. We will now open the floor for questions and discussion. So please type your questions into the question pane on your control panel, and I will do my best to pronounce her name correctly. The first question is from Hillary Whitcomb. She asks, What's going to happen when CFCs dissipate appreciably over the next 20 to 30 years? My understanding is one CFC molecule warming potential is 1,000 times of a carbon dioxide particle, and that in about 20 to 30 years most will be gone. Are those changes and associated cooling accounted for in projections?
That's an excellent question, Hillary. And when we look at CFCs into the future, those reductions are taken into account in the climate models. And I know in the next series of climate models that come out, we have a much better idea of how quickly the CFCs are going to dissipate with time. And so they will be taking them into account much more at that point in time.
Okay, thank you. All right. I don't see any other questions typed in yet. Sometimes it takes a couple minutes. I have a question for you, though.
Okay.
You had said that in if precipitation the winter before a fire season, if you have more precipitation in the Southwest, that means you could have more fires, but in the Great Basin, you could have less?
Yes, that's correct. In the Great Basin, the fire tends to be climate limited. And so if you have a moist climate, then that's going to increase the fuel moistures in the area, and that will, particularly in the northern Great Basin especially, that will decrease the chance of fire occurring. In the Southwest, you're fuel limited, so you don't have that connectivity between plants that you do, and so if you have a year that's extremely moist or you get a lot of rainfall, you're going to increase the connectivity with the annuals and grass species that can move in, and that's going to be able to sustain your fire across the landscape in a dry year following it.
I see. Thanks. All right. Does anyone have any more questions? I don't see any typed in. Well, I guess you answered everyone's questions, Faith Ann.
Great. Thank you.
All right. Well, a recording of this webinar will be sent to you automatically through the GoToWebinar system tomorrow, and it will also be posted on our Great Basin Science Delivery Project website. And as always, if you have questions that come up later, you're welcome to email me, and I can forward those on to Faith Ann. And also, if you have ideas for webinar topics, please also email or call me. All right. Well, thank you so much for your presentation today, Faith Ann, and thank you all for your participation.
Thank you very much.
All right. Have a great day.
All right, you too. Bye-bye.
Bye.